Hello again. Welcome back. Still on chapter 16. Okay. The last section that we just did, Coulomb's law, was very quantitative. A lot of trigonometry, a lot of algebra. Okay. I really hope that you guys did those examples, 16.2 through 16.4, and followed along with the slides or followed along with the videos that are posted on Canvas. Okay. Those are really important examples to do. I shared with you in that video how I would turn those examples into homework problems. So you should be a master at those examples to I'm sorry, I said a homework problem. I meant a test problem. How I would turn those examples into a test problem. Okay, so mastering those examples is going to be important for being ready to, tackle any kind of test question that I throw at you in regards to those examples. So now we're going to get a little more conceptual again. All right, so 16.4, really quantitative. 16.5, a little bit more conceptual. So we are going to talk about the notion of the electric field and how it helps us visualize the way charges exert forces on each other. Okay, so we saw, that two particles separated by a distance exert forces on each other. And it's kind of strange because in physics 1, the way that we exerted forces on objects is we were touching them, right? We were pushing a block, or, we were spinning around in a circle, or driving a car on a road or something, right? And the force occurred due to contact. But what's really cool is in electromagnetism, and even in gravitational force, right? You can exert a force on something else, at a distance, kind of like a magic trick, right? Kind of like telekinesis, right? You can exert forces on other objects just by being near it and not having to touch it. So we can describe forces that occur at a distance through a concept of field. So when we're going to talk about the electric field, okay, which is describing how the electric force affects charged particles. But if it helps you, you can think about the gravitational field. You might have a little bit more comfortability and more intuition about gravity because we are, walking around on Earth all day, right? So we kind of have a good understanding of how gravity works, right? Gravity is what keeps our feet on the ground. If we didn't have gravity, every time we took a step, we would be bouncing and flying off, okay, depending on how weak the gravity was. So I want you to imagine two charges, okay, next to each other, just like we did in the previous section, except now we're going to call them big Q and little q instead of Q1 and Q2. Okay, so we have big Q and we have little q. Okay, and we're going to be talking about little q and what he feels, right? The force that he feels. So therefore we draw the force vector on him. We're going to be talking about what little q feels due to the presence of big Q, right? So if little q and big Q are both positive, right, they're both positive charges, the force that little q feels due to big Q, well, he's going to feel a repulsive force, right? He's going to want to get the heck away from big Q because they are the same sign. So the force vector will point in a straight line path directly away from big Q. Okay, right? That's what we just talked about in the previous section. What I'm going to tell you now in this section is that instead of talking about F and little q, we can ignore little q. And we can say that at that point where little q was, there's an electric field there. And that electric field, if we were to put something there, that electric field would be responsible for moving Q. Okay? So picture, right? So if we read these, this is kind of what I just said in these boxes, right? To explain how big Q exerts a force on little q at some point P, we can picture charge big Q as producing an electric field at point P. And that field is there whether or not little q is there, or 3Q is there, or negative 50Q is there, right? That electric field is there because big Q is present. And if we're anywhere near big Q, we're going to feel a force. But we do, as you know, that force that we feel, it depends on what that charge is at location P. And so that's why the electric field is a really good way to talk about electric force, because you don't have to talk about both charges. You can just talk about one charge, the charge that is producing the field, okay? Or the charge that is putting the force on other things, big Q, okay? And so, well, there is a relationship between force and electric field, and it is very simple. The force that little q feels due to big Q, well, that's just little q times E, okay? And if they're both positive, that force direction is going to point to the right. And if little q happens to be negative, that force direction is going to point to the left. But E will still point to the right. What's flipping that force vector to the left is the fact that Q is negative. Okay, so the force on charge Q is in the direction opposite to the electric field if little q is negative. And that force is going to point in the same direction as the electric field if that little q is positive. Okay, so this is the concept of electric field. So the electric field is there to allow us to generalize the force that big Q would exert on any arbitrary charge that we put near it. Okay, any arbitrary little q that goes near it. And that's why we call little q, we call this guy the test charge. Okay, he's called a test charge. Because, you know, it doesn't matter what charge he is. The electric field is still the electric field because this electric field belongs to big Q. Okay, this electric field is associated with big Q. And I'm gonna show you what the functional form of that electric field is, and it'll make sense, right? The electric field belongs to big Q. The force is in terms of little q. Okay? Let that marinate in your mind. So the electric field, let me just erase this from my other class. We'll get to that, right? So the electric field and the electric force are related quite simply. The force that a charge little q feels in the presence of big Q is little q times E, where E is the electric field created by big Q. And you can rearrange this, okay? You can rearrange this. You could say that the electric field, this is not as intuitive, so don't worry about this way, okay? And the vectors kind of came out bad, sorry. This is not as intuitive, but I mean, you can do it. It's just mathematically, you can certainly rearrange it this way. The electric field can be thought of or interpreted as a force per unit charge. So that's how you can imagine that electric field is a general way to talk about forces, right? Because we're taking the force that those two charges exert on one another and we're dividing out by one of the charges, okay? In a way to generalize us talking about the force between two charges. We're just going to talk about one charge, that charge being the one producing the electric field. Okay, so from this we can see the units of electric field. They're newtons, right? Force per coulomb. Charge, right? Newtons per coulomb. So you could think about, here's another way to kind of express this, right? If a 1 coulomb charge experiences a 1 Newton force at a certain point in space, well, then there's an electric field right there of 1 Newton per coulomb. Okay? So these equations, this is just kind of a little caveat, okay? But we're not going to, really be dealing with anything other than this idea. This is only strictly valid, mathematically speaking, if the particle, little q, is a point charge, okay? Very small. And that's because the electric field can be different in different places. So, right, here's our big Q. He's responsible for creating the electric field. And if he's positive, well, this is what his electric field vector, and we're going to look at this, I'm just going to tell you a little bit ahead of time, right? This is what his electric field vectors are going to look like. They're going to be really strong. So they're going to have a big, long magnitude right here. And then the farther away you get, the little, field vectors are going to get smaller. They're going to be weaker, okay? Because the electric field gets weaker the farther away you get from the source of the field, okay? And so that's why it's important that we make little q a tiny little point particle, because if he was big, well, then he would feel a different field vector. He would feel a different electric field over all his points, and we'd have to do a bunch of crazy math to average all that out. So this is why we need to imagine little q as being small, so that he feels the electric field, one value of the electric field. And you know what I mean? We don't have to average, okay? So that's the point of that. In this slide, this is just talking about if you want to compare the notion of gravitational field with electric field to help you visualize and be comfortable with this notion of electric field. Okay, so if you want to, think about that, read through that slide. I'm not going to go through it, but if you need that intuitive grounding, there is a one-to-one notion between gravity and electric field, gravitational field and electric field. So this is a good slide. These slides will pop up from time to time. Okay, this is going to make you aware of some very common misconceptions that occur throughout our whole class. Okay, so this is number one. It's very common to want to make your force and your direction your direction of your force and your direction of your electric field in the same direction, but they may not always be in the same direction. Okay, so if you remember in the first slide we looked at, we had big Q, little q, right? And so we said that big Q was going to be positive, and then we had little q. Here's positive little q. Again, let's let big Q be positive. What if little q was negative? Okay, well, guess what? The electric field vector at this location is going to be pointing to the right no matter what, because the electric field vector belongs to big Q, okay? However, the force vector, well, if little q is positive, the force vector will be to the right. If little q is negative, the force vector will be to the left. So you can see how the force vector can change directions, but the E field, which belongs to big Q, is always going to be the same direction, okay? So in this example, 16.5, we'll be determining the charge to mass ratio. I want you to go to Canvas and look at that example video and follow along there, and then come back to this video and resume the lecture. Okay, so what is, why are we learning this? Okay, why are we learning electric field? Why do we need to know this? Well, some of you may encounter this in your future studies. It's a process called electrophoresis, and this is a technique that is used to separate molecules, okay, according to their charge and their mass. All right, and that helps you identify molecules. And there's a very important application of electrophoresis. Electrophoresis is a very general term, but old DNA methods, DNA profiling, right, is a very specific example of electrophoresis. And so here's how it works, right? So you have your unknown solution, right, your sample that contains different kinds of molecules, and you put it on a piece of paper. You dab a little bit at the end. Then you apply an electric field in the vicinity of the paper, and you're going to have molecules of different sizes and charges migrate along that film depending on their ratio of Q over M, right? Because remember what we just found out is that Q over M equals A over E. So depending, you can vary the electric field, and you can see how far the molecules go and help you identify them, okay? And so this is basically an application. Doing this example is giving you all the information you need to know to fully understand how electrophoresis works, okay? So there's other examples of electrophoresis, like determining if something is counterfeit ink, detecting HIV, and then, of course, DNA profiling, right, and forensics. So very interesting. So, I mean, there's, as I was telling you before, there's a lot of very cool applications of physics too in your fields. Okay, you will find it everywhere. Let's examine the electric field for a special case, and that is the electric field created by a point charge. So we've already talked about this point charge. We called him Big Q, right? And we're going to look at the electric field that he creates, which influences any other charge we put in its vicinity, okay? So we saw in equation 16.2, which was this. Okay, it told us how a point charge, little q, responds to an electric field that it's sitting in, right? So it feels a force, okay? So if little q is sitting in the vicinity of another charge, that other charge will be producing an electric field, and little q will be feeling a force as a result. We can also use that test charge, little q, to figure out what the electric field might look like around a charge, big Q. Okay, so we're going to assume that they're both point charges. So we take this little q and we kind of stick it around in different locations, and we can measure the force that the little q feels, and then we can convert that to electric field by just rearranging equation 16.2, right? So let's examine that. So we basically, stick a point charge, let's say really close to big Q, and we measure a force on it, and if they're both positive, the force vector will point in a straight line path directly away from big Q. Well, if we divide out by little q, that's going to give us the electric field. Okay, so if the black is F, we divide the black vector F by little q, the result would be the electric field. Okay, and if we look at this picture closely, what you can see is that if you're close to the electric field, you're close to big Q, the electric field vector is pretty big, right? That's the magnitude. And the magnitude is large. Compared to, for example, when you are just, when you're a little bit farther away, okay? Look at your magnitude. It's a little bit smaller. And then if you're even farther away, look at the magnitude of E, it's even smaller. So what we can see here from this picture is that the magnitude of the electric field, it's inversely proportional to the distance you are from the charge creating the field, in this case, big Q, okay? And it turns out that it's actually inverse square proportionality. So that's pretty much what this slide tells you, right, is we see that inverse proportionality. We use little q to determine the electric field by simply dividing, the force by charge, okay? And we see that we have this proportionality, this fact that the electric field is also proportional to the distance squared, much like the force is, right? We already know. Actually, we could just kind of do the math right now. Okay, we know the force between two charges. We know it as K little q big Q over R squared. Well, when we divide by little q, as we do right here, the little q drops off, and all we're left with is big Q, right? And this is the equation for an electric field due to a point charge big Q. It's simply K big Q over R squared. And the little q has disappeared because that is our test charge and we divided it out in order to define the electric field. So, right, so the force, between the two particles changes with distance according to Coulomb's law. Well, the electric field should do the exact same thing because the relationship between electric field and force, it's only off by a Q, which is a scalar quantity, right? It's just a number, a value. So it's their functionality of E and F are identical. They're only off by a factor of Q. So visually, so what we saw here, right? Visually, electric fields are vector arrows that exist anywhere in space around a charge, okay? We can examine the density of electric field lines, and that can give us a clue of how strong the charge is, okay? How large the charge is. And so low density around a charge would indicate a small charge. High density of electric field lines, okay, a little bit bigger. And then here you can see even higher density of field lines indicate a larger charge. So let's talk more about, the visualization of electric fields, okay? There's a rule we're going to use, and this rule is, it's another rule kind of like the force rule. And that gives us the direction of the force. Well, to find the direction of an electric field, all you need to know is that field lines created by a positive charge point directly away from the charge. Field lines due to a negative charge point directly toward the charge, okay? And so that's why if we scroll back up to this figure, here we have a positive charge and you see the field lines are pointing directly away. Here we have a positive charge and the field lines are pointing directly away. Okay, and the field lines, in this picture, it's hard to see, but the field lines exist at any point in space, right? Here we're just drawing them originating from right here, super duper close to the point charge. But in reality, there's an infinite number of electric field vectors at any point in space that I choose. There will be an electric field vector. Now, the farther away I get, they'll get smaller and smaller, right? Because they are related. The electric field magnitude is proportional to the distance squared, inverse distance squared, right? So anywhere I draw, I'll have a little field vector, but the farther away I get, the smaller they get, okay? Now, for negative charges, that field vector line, it's just always going to point directly toward the charge, okay? So these are all going to have the same magnitude because I'm drawing them at the same R. Okay, if I went a little bit closer, their vector arrow would be a little bit bigger. If I went farther away, the vector arrow would be even smaller, but it would still point directly toward the negative charge. So caveat to think about, right? Every time I've drawn these pictures so far, those vector arrows have been in 2D. Well, that's just because I'm on an iPad and I'm drawing on a two-dimensional thing. But in reality, electric field vectors exist in 3D space. So much like these images rendered here, right? You can see the electric field vectors are existing everywhere in three-dimensional space. Now, finally, let's get to the qualitative part. The quantitative part. What is the equation of an electric field? Okay, we talked about the fact that, the farther away you get, the weaker the electric field is, the stronger Q is, the stronger E is. So there we go. It looks just like Coulomb's law, doesn't it? Except it's missing a Q. Right? It looks just like Coulomb's law, but it's missing a Q. Well, and remember Coulomb's law? Or, well, let's just write it both ways. KQQ over R squared, right? That's the force between little q and big Q. Well, remember that we also know that F is QE, and there you go. You can see the E which belongs to big Q, is KQ over R squared. Well, guess what? That brings us right back to Coulomb's law. Let me write like this, Q, KQ over R squared, right? You see that? The equation of electric field looks just like Coulomb's law because it's a part of it, right? It's a part of Coulomb's law. That's why electric fields are a way that we express force. Okay? So instead of, writing, it's like, doesn't save us a whole lot of time, but instead of writing QQ over R squared, we can write little QE. Okay? So that's the connection there. So this is the equation for an electric field. So you're going to get some questions in the chapter 16 homework that asks you for the force of something, and you're also going to get questions that asks you for the electric field of something. And it's really easy to get those two confused. So when you understand fundamentally the difference between them and how they connect together, you're going to be very successful at these kinds of questions. Okay. So, and recall, okay, so there's the magnitude, right? This is a magnitude of the electric field vector. The direction is going to be given by the rules, right? Just like how we broke Coulomb's law into magnitude and direction. Electric field, magnitude given by this equation, direction given by the rules. The rules being pointing radially outward from a positive charge, pointing radially inward for a negative charge. Okay? Those are the two rules that you use to determine the direction of the electric field. So electric fields are vectors, so are forces. And they're going to obey all those mathematical properties, meaning that they can be collectively added together or individually added together, right? At any point in space. So if at some point in space you have, 85 field vectors or force vectors, F85, okay, F62, you can add them all up at that point. They don't interact with each other. You just add them up to figure out what the total is. And the same goes for electric fields. So that's all this slide's telling you. It's the principle of superposition. I don't know if you remember that from Physics 1. All right, this is essentially explaining the principle of superposition. So here we go. Let's do this problem. It is also on Canvas. I'm gonna kind of get you started on it, okay? I'm gonna give you, actually, you know what I'm gonna do? Because you have this problem on Canvas, you can watch the video for that. I'm gonna give you the test question version of this problem, okay? Oh my God, get ready. So take a moment to read the problem. I'll read it with you. We have a point charge Q1 that's placed 0.5 meters to the left of another point charge Q2. Okay, so we have 2 point charges separated by a distance of 0.5 meters. And in the test version of this problem, instead of having Q1 and Q2 different values, I'm gonna let them be equal just for simplicity, okay? So we're gonna, different from the problem as is written here, we're gonna let Q1 equal Q2. And what we're gonna do is we need to find in what region 1 here, region 2 between the two, region 3 to the right of Q2, in which of these three regions is it possible for the electric field to be 0? Okay, so here's the test version. Q1 equals Q2. Which region could the electric field be 0? So we don't need to quantitatively calculate anything like in this example, but you should do it because it is a good exercise for you. And there is, other ways I could ask this question that could involve calculations, okay? So like I could just another thing to throw out at you is I could say, okay, well, right here, what is the total electric field right here? Well, then you would need to calculate it, okay? So, but for just to kind of illustrate conceptually how to tackle this problem, we need to figure out which region the net electric field could be 0. Okay? So E will be pointing to the left. And now for green, for Q2, the electric field to Q2, well, it's also going to be pointing to the left, but it's going to be farther away from this point, right? So its magnitude is going to be smaller, right? Because the larger the distance, the smaller the electric field. So we're going to have a net electric field pointing to the left. So is it possible for these two to add to 0? No. No. Okay, so we know that region 1 is not possible for them to add to 0. So what about let's skip region 2. Maybe you're seeing the pattern here. Let's skip region 2. We're going to go back to region 2. I think you kind of see why already. But let's follow through now. Okay, let's do region 3. Electric field due to Q1 at this point right here. Pointing directly away, right? Because he's positive. Well, and he's probably going to be small. I want to erase the purple. All right, well, we'll make him small, right? Because E due to Q2, which is also going to be pointing, is going to be a little bit bigger. Why is it bigger? Because he's closer, right? Q2 is closer than than Q1. And so is it possible for these two to add to 0? No, cannot add to 0. Oh, but now what about region 2? Okay, obviously we're going to get something here. So we're going right in the middle. Q1, electric field due to Q1, going to point directly away from Q1. Electric field of Q2, going to point directly away from Q2. So is it possible for these to add to 0? Yes, they could. Okay, and where do they add to 0? Well, technically they add to 0 right in the middle because I made Q1 equal to Q2. All right, but even if I didn't, even if I said Q1 is greater than Q2 or Q2 is greater than Q1, somewhere in this region it is possible for them to add to 0, okay? Somewhere in this region it is possible because the vectors are going to be pointing in opposite directions. So somewhere, I picked the middle, but somewhere in there it can add to 0. And that's where this example comes from. This example wants you to find out exactly where, okay? But in the test version of this problem, I'm asking which region, and so by process of elimination, there's nowhere that those could add to 0. Only in the middle could they add to 0. And so other variations would be, well, what if I made one negative? Okay, so there's going to be other variations that could be asked on the exam. Okay, so I want you to do this example, follow the video on Canvas. And there's also a homework problem that does this as well, that asks this question. Okay, so here we go. Triangle, another triangle question, okay? Follow the same steps as in the example calculating electric force, okay? So, except now we're doing electric field. So you can see, just look at the triangle there. Look at those vectors, right? We're doing the same kind of math here, except we're going to follow the rules for electric field. And you can notice that at the top of the triangle, we don't have a point charge anymore. We just have a point in space. So when you are done reviewing or going through that example, come back to this video at this point. Okay, and we're going to talk about one last thing in relation to electric fields for the end of this section. So we're going to look at electric field lines, okay, in a little more detail. So this arrangement here, this is called a dipole, and you've probably heard of dipole before if you took chemistry, okay, or if you took even advanced chemistry. You've definitely heard of a dipole. What is a dipole? It is two charges of equal magnitude but opposite sign, okay? And they're just separated, symmetrically. So the field lines of a dipole, well, we know that electric fields point away from positive charges, and go towards negative charges. So that's exactly what would happen here. It would point away from the positive charge and go feed right into the negative charge, okay? And so the farther away you go, you can see that the density, right, gets smaller, and so then the E field gets weaker, okay? Closer you are, the stronger the electric field is. So let's look at this conceptual problem. So the positive charge in the dipole shown in the previous picture, okay, it's attracted to the negative charge. All right. To find this force of attraction, the electric field that we would use is what? Which one? Okay. So remember, F equals QE. So this is the charge that feels the force. And then in the electric field, this electric field, which remember is KQ, big Q over R squared, that Q is the charge that exerts the force. So let's read the question again. Okay, the positive charge is attracted to the negative charge. So we're talking about the force that the positive charge feels. So this is going to be the positive charge. So then, to find the force of attraction, we need the electric field to talk about the negative charge, right? So the field due to the negative charge. That's what electric field we would use. Make sense? The field due to the negative charge, because of these definitions right here. Right? If you get this, a concept, you are good. You are good to go. You understand electric fields. Okay? Suppose that both charges were negative. Okay, so suppose that it's not a dipole, it's just, we just read for negative. Suppose that we had two charges, positive, separated by some distance d. I believe that's what the question is asking. At point P in that figure, all right, so let's say these are both positive. That would be cute. I'm not going to do that. Beep, beep, beep. Oh, well, they use blue. Let's change it to blue. Blue. Okay. What direction would the electric field point? So remember that's the way they pointed for the example. All right. What direction is it going to point? So let's do one at a time. So E field due to Q on the left. Okay, leftmost Q. What direction is his electric field vector going to point? At location P. So Q is positive. Electric field will point directly away, straight line path, just like in the force, but this time we're talking about electric field, straight line path directly away. So here is E due to the left guy. Okay, what about the right Q? At location P. Electric field, straight line path directly away because he's also positive. Okay, straight line path directly away. So here is E right. If we add these two vectors together, well, if we break them into components, you can see that the x component of the left, of the right, oh my God, ERX, x component, right? I'm breaking this vector into components, x component, y component of the right, x component of the left vector, y component, boom, you can see L, Y. You can see that these two guys are going to go, they're going to cancel, and they're going to add up in the Y direction. So the net direction is straight up. Okay, this is exam style question. Okay, straight up. Oh, straight down. Oh my God, wait. What do we do? Oh, we're both negative. I'm sorry, I did positive. Oh, okay. I misread it. I'm sorry about that. I misread, but it's the same. It's the correct answer, right? I did it for positive. I'm sorry. But let's do negative too, okay? That's positive here. My bad. And I'm not going to like start over this video because I know like nothing will ever get published. So let's do negatives. We'll do it. We're going to do both ways because I love you and that's what we're going to do. So here's our triangle, both negatives. Red is negative, point P. All right. So remember, electric field vectors point directly toward negative charges. So electric field vector for the left guy, electric field vector for the right guy. The X components are going to cancel, right? Because one is in the negative X, one's in the positive X, and then boom, net the components, the Y components of each one, they're going to be directly on top of each other, are going to be pointing directly down. So that's the correct answer for this conceptual problem. I'm sorry, I answered the wrong one. So, okay, you can see that. Okay, there we go, straight down. So, to wrap up our little foray with electric fields, okay, any charged object produces an electric field in space around it, and any point around it, right? So any charge Q, okay, let's just say it's positive, he's going to have an electric field vector right here pointing directly away. He's going to have an electric field vector right here pointing directly away. He's going to have an electric field vector right here, right here, right here, pointing directly away. The size of this is going to depend on how close we are to Q, okay? The farther away you are, it's going to be small. The closer you are, it's going to be big, okay? So, and then the magnitude is given by something that looks just like Coulomb's law, okay? And then the net electric field of two or more charges, we can add those vectors together, okay? Basic stuff. So that's the end of 16.5. I'm going to make another video for the following sections.